Hello again. So in this video, I will start introducing Riemann integral, which is a very old but very foundational integration, a way of integration. Okay, there are a lot of definitions, and I think this video gonna be short because there's no long proofs or anything. So let's get started. Okay, so first of all, we introduce the motivations, right? So if you have a function and you want to compute this integral as x ranges from the interval a to b, what is area of this? Well, there are very intuitive ways that you write some rectangles. You can see my blue rectangle and my pink rectangle. And where the blue area is certainly lower than the black area and the pink one is above. So what we want to do is we want to compute the blue one, we want to compute the pink one, and we want to take the limit as the bar goes narrower, narrower, and narrower. And then hopefully you can find the limit, and that limit is equal to Riemann. So that's a very rough idea about Riemann integration. Okay, let's talk about the definition. So here, this is a partition. So notice that partition is a collection of points, or you can, it is a set of points. The order doesn't really matter, but you need to indicate 0 or right? So, and then x0 is always equal to a, and as last xm is always equal to b. So here should let it be. So I don't say there's no complicated things about partition. You just need to remember, given you an interval AB, how are you going to partition it? How are you gonna cut it into different pieces? And at each joint, it is an element in your set of partition. And you have to include the beginning, which is A, and the tail, which is B. Yeah, okay, and then let's define the delta xi. So once you define the partition, it is natural to define the length of each partition, right? So what is the length of this? What is the length of this? And what is the length of this? So that is xi is equal to delta xi is equal to x minus xi minus 1. Later we'll see there is kind of like a weighted version. It's called Riemann-Stieltjes. It's called Riemann-Stieltjes integral. The only difference is that here we have xi minus xi minus 1, but this is actually a function. So alpha is a function, and we input xi into that function. So this is a different number than xi, and this is different number than xi minus 1. And then alpha doesn't have, it could be any function as long as it is monotonically increasing. Okay, so assume f is bounded on AB, right? And so at this point, we only deal with integration from A to B. We're not talking about, for example, negative infinity to B or A to positive. So we haven't started doing that yet. This is our assumption. And then let's define MI and the small mi. So mi is what? This expression, remember it just, for example, in our paragraph here, if you look at this region, this interval, you find what is the maximum and you find a supremum and you find a minimum. So here supremum is this. Therefore, mi, the capitalized mi is this point. And this is lowest point in this interval. So this is a small, this lowercase n line. Okay, and let's define the upper Riemann sum and lower Riemann sum. So upper Riemann sum is the summation of the all the pink boxes that I draw here, all the pink boxes, which is defined in this way, summation. So you first partition your interval into different pieces, and then at each interval you're looking at the supremum point in that interval. Again, for example, in this interval, the supremum is going to be this point. In this interval, the supremum is going to be this point. And in this interval, the supremum is going to be this point. And you make those as a height of the rectangle, and you sum the rectangle altogether. And that's what this expression is talking about. And similarly, for the lower Riemann sum is you have the partition and for the lowest point, right? So here's this low point, here is this low point, and here this is lowest point. And then you draw the blue rectangle, and that is a lower sum. Okay, of course, both of them depend on the choice of partition. And again, in order to find the limit of them, whenever we say the limit of the lower sum or the limit of upper Riemann sum, we're talking about the limit as we change the partition. Okay. Another definition is upper Riemann integral. So we recall before is upper Riemann sum. Here is upper Riemann integral. Upper Riemann integral is where it start taking the limit, which sort of limit, but infimum among all the upper Riemann sum over all possible partitions. And lower Riemann sum is you are taking the supremum of lower Riemann sum over all possible partitions of the interval. And because we're comparing them and we find an infimum result, it does not depend on P. And because we're comparing and we find the maximum or we find the supremum result, the final result does not depend on P. Okay, another definition is if there exists this, so the upper Riemann integral is equal to the lower Riemann integral, then we say that f is Riemann integral. And the Riemann integral of f is exactly equal to this. And a fundamental question is which function belongs to space R, where space R is a Riemann integrable function. It is a complicated question, and it will be fully discussed in after we introduce metric theory, actually. But now, later we will introduce 3 sufficient conditions such that the function is Riemann integral. So just like very interesting question to keep in mind. And if you study metric theory, it should be covered in the first 2 chapters. Okay, and then the remark. Remember that when we were talking about delta xi, I mentioned about delta a alpha I, which is equal to alpha xi minus alpha xi minus 1. Here alpha is a function that takes xi or xi minus 1 as input and output a real number. So here, just like a little bit more about that. So here, an alpha is a function, it's monotone, non-decreasing or increasing. So we have this, and f could have jump, it could be continuous as long as it's monotone, non-decreasing, then we're fine. And there's some examples. So this is definitely monotone, non-decreasing function. So are those okay? And then for this, for example, this is function looks like a jump, right? So it is equal to 0, and if x is larger than 0, it is equal to 1. So this is the So that is the so that is an example about such function alpha. Okay, and, we redefine. So we redefine basically everything we defined before, we just in terms of alpha here. So here, because we're using the function alpha, we specify the notations. So here the alpha, 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 and f is Riemann integrable with respect to alpha. We find only if these two are the same, and this explicit Riemann integral of f, again, those are with respect to alpha. Okay, and partition. So refinement means just like if you have partitions and the one partition is a subset of the other partition, so the larger, then the partition contains more elements. And also the partition that contains the smaller set of partition is called a refinement of the partition. So for example, P1 union P2 definitely contains P1. So P1 union P2 is a refinement of P1. Similarly, P1 union P2 is also a refinement of P2. Okay, and then we have upper and lower sums. So when we take a close look at the upper and lower sum of the integral, so there's a lemma. So if we have a refinement of partition, then the lower sum of f with the first partition is going to be, with the second partition, with the refined partition, is going to be larger than the lower sum of the original partition. And the upper sum is going to be smaller than the upper sum of the refined partition is going to be smaller than the upper sum of the original partition. So that is the claim. And I won't go over the detail. You can pause the video and check my work. I will state the basic idea and the outline for this proof. So since you are trying to show, right? Since you're trying to show that, for example, the lower sum of using a refined partition versus the lower sum of f using a regular partition, right? So you're trying to compare those two, and what is the difference between the first term and the second term? Well, the only difference is that the first term contains an extra element. So when you look at the graph here, it has a P star actually has an extra Y set versus the original partition has only doesn't have Y in it. So the difference, like we'll try to compare which one is larger, which one is smaller, the difference is gonna happen in this around here, right? So that's so intuitively it's natural to think about it, think about how what aspect of this part contribute to the difference of this two values, right? So what we did is because our intuition feels like this value is larger than this value, so I put this value just in front. Hopefully we can get a positive number as we guess. So where this, we use a partition. So we use this partition, and to write it because we do want to subtract the things that already contained here. So the way I wrote here is first, this is something that is common in this term. So for instance, this term is here, and I write it in terms of two parts. So the first part is this, which you can find in this term. And those are the extra special term. And write it out. Okay. And then this is just by the definition of this. Okay. And then so notice this and this has a lot of common things. That's why I wrote the first term in two different parts, in this part and in this part, because I want to you notice that this has a lot of redundancy with this one. And because there is a subtraction, a lot of things are canceled out. So I got this expression. And once I got this expression, I notice if I can combine more into kind like in a simplified way, which is introduce this. So the minimum between this and this, right? So now I have, so now the first expression and the second expression has a common term. Okay. And then therefore we can combine this common term and we have this minus this, which is yeah, we didn't do anything else. We just combined the two terms together because they have the same parameter right now. Okay, and this actually after doing the algebra, it is equal to alpha x I minus alpha x minus 1. And again, this and this are the same, therefore we can combine, and therefore we obtain this. And by definition, since xi is larger than or equal, xi is larger than xi minus 1, and alpha is monotone decreasing function, so this is non-negative. And for this one, it's just the property of increment, right? So notice that you're comparing increment in this interval, and this interval. And because if you draw the I minus 1, y and xi, and you're comparing the increment here, but the minimum between the increment of this one and this one, and you then later compare the increment of the whole interval of this one. And intuitively, you can also prove by definition, but it's pretty straightforward that this expression is non-negative. And therefore, the whole thing is non-negative. And notice that what we've done here is we just compared two different partitions, but in general, we should compare any refined partition than P. So this doesn't have to be one. K, where K is a natural number. You can use induction for that. Okay. And let's now introduce study a little bit more of the upper and lower integral. There's a fact that this inequality holds no matter what partition you're using. So the goal, in order to prove this, well, let's see how to prove this. You're trying to show a relationship between the lower sum and upper sum, right? And the lower sum is equal to what the summation of lowercase mi times delta xi, and the upper sum is equal to the summation of capitalized mi times delta xi. And when you take the difference of those two, it boils down to compare what is mi minus uppercase mi. And because lowercase mi and uppercase mi, they are two values in the same interval made by the partition, right? So when lowest was highest, so of course capitalized mi is larger than lowercase mi, so that's why this inequality always holds. But the another question is, what about this inequality? It is not immediately seen because this involves with like in ink and soup. So usually it's not clear after you're taking the limit or after you're taking the limit or after taking ink soup or anything about the income or suprema. So we have to prove that, right? And how to prove that? Well, you need to remember the definition for this. What is definition? Well, that is the supremum of lower sum over all partition. And this is the infimum of all upper Riemann sums, right? So we want to show this, and because this is infimum over all partition, this is so sorry, this is supremum over all partition. This is infimum over all the partitions. So you are trying to, no matter what partition, no matter, it doesn't have to be the two partitions you use for the left and the right hand side. You need to show that it doesn't have to be the same partition, but the inequality still holds. And how to show that? Well, we can um, find a refinement, so common refinement partition, which is a union. And because by this fact, is the refined partition will always have this hold, right? And also because of this is refinement, and this is the one that is not refined by, so this fact, this is fact 2. Let me actually write them in. So this is fact 2, right? And this is fact 1. So here we're using fact 2. Okay, and here we're using fact 1. And here we're using fact 1. So fact 1 is talking about comparing the lower sum with a lower sum with a refined partition. Upper sum with the upper sum with refined partition. And fact 2 is more about comparing lower sum and upper sum for any partition. Okay, so that is our inequality, and then at the end we obtain, because this holds for any P1, this holds for any P2, as long as this is the relationship. So what do we have is the conclusion is this is smaller or equal than this for any two partition. So 2 and P2 can be any partition. And therefore we can take the infimum on both sides. If we take the infimum on this side, if we take the infimum on this side over all the partitions, P2 does not affect. This is a fact. Let me think. No, because we're doing infimum over P2, where P2 is changing. And here is a variable P1. We can think this as a variable. Since this as a variable, this as a variable, we can think as this is like really the quotation limiting behavior with that variable P2. So this one does not affect, and this one becomes this. Then after that, we have take the supremum, so which is another quotation limit behavior with respect to variable P1. So on the left, we have this. On the right hand side, it does not depend on P1, therefore it is just what it is. So it's already done. And therefore, at the end, we obtain this smaller equal than this. And therefore, finish the proof. Okay, before I end the video, let's just do a summarize about what we did in this lecture. So, okay. So definitions. Riemann integral. Okay. Partition P delta x I delta alpha I. That's Riemann. I maybe spell this wrong. Let me double check. Let me double check. So ST I E L T J E S integral and lower Riemann sum upper Riemann sum, and then we also lower Riemann integral upper Riemann integral. Okay. What do we have? What else do we have is we have Riemann integrable. And we have some propositions, right? So the first one is L F L P F alpha is going to be smaller. It's going to be when you put that L P star F alpha. U P F alpha is going to be smaller than that F U P star F alpha and P star. The refinement, which means P. Okay. And the second one is we're going to compare lower sum and upper bound. So for our P, L P F alpha is smaller equal than P F alpha. And then for three is lower sum FD alpha is smaller equal than upper Riemann integral. Lower Riemann integral. This is upper Riemann integral. So A, B, F, E, alpha. And then I think that's it. Thank you for reviewing this together with me. And let me know if I made any mistake or typos.